Hey guys, in today's video we're going to be learning about the concept of enthalpy and also learning how to analyze potential energy diagrams to determine the change in enthalpy over the course of a chemical reaction. Now if you remember, enthalpy is effectively the chemical potential energy of a compound. If we look at a compound's potential energy, we can ascribe its stability. The lower the potential energy of a compound, the more stable that compound is. So lower enthalpy compounds are intrinsically more stable. Now, what does this mean? Well, over the course of a reaction, we can actually track the change in enthalpy of reactants to products. The change in enthalpy. Anytime we see change in enthalpy, we're represented by a delta, delta being a little triangle, Greek symbol delta, delta, and the H. H is our variable for enthalpy. So delta H represents the change in enthalpy over the course of a chemical reaction. Now we can use a change in enthalpy to determine quantitatively how much energy is either going into a system over the course of the reaction or coming out of a system in the course of a reaction. When I say the word system, what I'm talking about are the bonds of the reaction itself. So the bonds of our reactants and the bonds of our products, all of that within the reaction represents the system. So if energy is going into the system, then we're going to have a positive delta H. If energy is coming out of the system, we're going to have a negative delta H. Now, if the delta H is positive, that represents what we call an endothermic reaction. Endothermic means energy had to go into the system over the course of the reaction. What this really means is that the potential energy of our reactants is less than the potential energy of our products. Over the course of the reaction, if we ascribe this to stability, the reactants thereby would be more stable than our products. So energy had to go in to be able to turn our reactants into products. In an exothermic reaction, our delta H would be negative. What this means is that our overall enthalpy of the reaction is going to be decreasing. Therefore, our reactants had greater enthalpies than our products. In the end, this means our products are going to be more stable than our reactants. And the change in energy there, that delta H, means it's leaving the system. So in an endothermic reaction, energy is entering the system from reactants to products. And in an exothermic reaction, the energy is leaving the system. So where's it going, or where's it coming from? Well, in an endothermic reaction, all energy that's going into the system is coming from what we call the surroundings. And the surroundings is kind of a generic term for anything around the system. And in an exothermic reaction, the energy is leaving the system and going into the surroundings. In the future video, we're going to talk about calorimetry, which is going to give more detailed descriptions of system and surroundings and how we can quantify that energy using the technique of calorimetry. So now that we've given definition to endothermic and exothermic reactions, let's take a look at energy diagrams to see how we can actually look at the change in enthalpy over the course of a reaction. As with any graph, the first thing we need to look at are the axes. On the x-axis here, we have something called the course of the reaction, or progress of the reaction. Now that seems kind of fluffy. It doesn't really have any quantitative function, and that's okay. Essentially what we're saying is, however long this reaction happens, at any point during the reaction, are we at our reactants on the left or our products on the right? All right, and in the middle, well, that's somewhere between the reactants and the products. So this progress of the reaction is kind of a generic term, not really quantitative in any way, shape, or form. On the y-axis, now this is the one that has a lot of power in terms of quantitative abilities. The y-axis represents the enthalpy, the overall enthalpy. So this y-axis on the left side represents, as it's flat, the enthalpy of our reactants. And on the right side represents the enthalpy of our products. So you can think of this as beginning of the reaction and end of the reaction. In the middle of our reactants and our products is a large hump. Now, in a single-step reaction, that's a single hump, but we are in the future going to see reactions that actually might have several different peaks in between reactants and products. We'll get to that when we get to kinetics. Those peaks in between reactants and products represent something we call the transition state or activated complex. Now the transition state or activated complex represents a molecule in between reactant and product. So this is kind of like if you're growing your hair out. When it's short, it looks okay. When it's long, it looks okay. But in between, you can never figure out what to do with your hair. It always looks kind of goofy, right? The transition state represents that middle ground. It's less stable, right? You inherently have higher enthalpy there because it's not a stable product or reactant. And so we have to kind of get past that in order to go from reactants to products. The energy it takes to get past that transition state, get over that hump, is represented by our activation energy, or E sub A. The activation energy is critical to any chemical reaction because the only reactants that can become products are those with sufficient energy to be able to overcome that transition state. Now let's take a look at one of these graphs when I fill in the actual reaction itself. The reaction here that we're showing is an endothermic reaction. Endothermic, I know because the delta H value is positive. Our products have a greater enthalpy than our reactants, so there had to be energy going into my system to go from my reactants to my products. In addition to delta H, we can also analyze this graph for something called the activation energy. Activation energy would be the energy that a reactant must gain in order to overcome the energy of the transition state that we just discussed a little bit earlier. So the activation energy would be the change in energy from my reactant up to the enthalpy of my transition state. So now that we've analyzed a potential energy curve, all right, let's take a look at the second one. Now in the second one, you'll notice that the forward direction here is exothermic, where C and D represent my products and A and B represent my reactants. Now I know it's exothermic because the potential energy of my products is less than the potential energy of my reactants. So in the forward direction, I keep saying the word forward, why? Well, that's because some reactions are reversible. All right? Some reactions are reversible, which means that not only can we move in the forward direction, where A and B are reactants and C and D are products, but we can also go in the opposite direction, where C and D become my reactants and A and B become my products. What does this mean in terms of delta H? Well, let's think about it. In the forward direction, this is an exothermic reaction because the products are going to be of lower potential energy than our reactants. But in the reverse, it's exactly the opposite. In the reverse direction, it's now endothermic. But what's awesome about this is the sign of delta H might change, but the magnitude didn't. So it's the same magnitude. The delta H is the same magnitude, just an opposite sign. The other thing we can look at in these reactions beyond just delta H, remember, is the activation energy. So it'd be the energy added to a reactant to get past the transition state's potential energy. So the activation energy, the forward reaction here, is the difference in potential energy between my reactant and the energy of the transition state. Now you'll notice, even though the delta H, the magnitude was the same in both directions, that is not the case for activation energy. In this exothermic reaction, the activation of the forward reaction is actually going to be less than the activation of energy of the reverse reaction. So if you look at the difference between potential energy of reactant and transition state in the forward direction, it's going to be less than the potential energy difference between the reactants of the reverse direction, which would be on the right side here, and the transition state there. So be aware, even though my delta H, the magnitude stays the same, in this, the activation energy does not. So I've got a practice problem that I want you guys to try. I'm actually going to have you draw a potential energy curve of the reaction I'm describing here below. So go ahead and pause the video, take a few seconds, see if you can draw the potential energy curve using numbers, so make it quantitatively accurate. Then when you're done, or if you get stuck, go ahead and unpause the video. When you get back, we're going to go ahead and go through it together. So now you've had a few seconds to work through this. Let's go ahead and work through it together. I've rewritten the practice problem here just so we can see it as we continue this process. First thing I'm doing, I'm drawing my Cartesian coordinate system and I'm going to label the axes. Remember, the y-axis always represents the potential energy, or enthalpy. All right, so I'm going to actually put it as potential energy. So I'm going to abbreviate that with PE. And the x-axis here is going to represent the progress of my reaction. Which means on the left side, I'm going to have reactants, and on the right side, I'm going to have products. I'm told that the potential energy of my reactants starts at -70 kilojoules. Okay? But I'm also told that it has a delta H of negative 800. So I don't want to start the potential energy way down here, because if it's going to then go down by another 800, it doesn't help me much. So be careful with that. I'm going to actually start my negative 70, like way up here. That's just going to represent where we're going to start, and it's all relative to each other, remember. So if that's going to be the potential energy of my reactants, I'm then going to have to figure out where do I finish. Well, if that's the potential energy of my reactants, and I know my delta H is negative 800, then the difference between reactants and products is negative 800. I have to go down by 800, which means overall, my products are going to finish down here. And I'm going to go ahead and label that. It's going to be at negative 870 kilojoules. How do I know? My delta H represents the change potential energy from reactants to products. That's going to be negative 800 kilojoules, which means there needs to be 800 kilojoules between reactants and products. Easiest way to do reactants, I'm just going to draw a straight line for a little bit. Now in every reaction, we are going to have some form of an activation energy. How high that peak is, hard to determine. And here, we're not given any quantitative data to tell me what the activation energy is. So what I'm going to do is I'm going to draw a somewhat ambiguous peak. It doesn't have to be super high or super low, but it has to be clearly an activation energy peak. I then continue this curve all the way down to my products where I draw another horizontal line. I'm now complete in terms of my diagram, except I need a label. So I've already labeled my axes. Now I need to figure out change in enthalpy. So my delta H is going to be represented by the difference between reactants and products. So what I'm going to do, I'm going to very clearly denote where it begins and ends. Okay, so there's my delta H, change in enthalpy. I'm also asked to do the activation energy. I'm asked not for activation energy in forward or reverse, so I'm going to go ahead and label both. Whether you did or not too much of an issue, but just be aware, remember, delta H is the same magnitude in both directions, but activation energy is not. So activation energy is going to represent the difference between my reactant and the activated complex, or the transition state. So I'm going to specifically denote my activation energy as EA forward. All right, so that's the activation energy of the forward reaction. In the reverse reaction, I'm going to do something very similar. So that's going to represent my activation energy in the reverse direction. So now what we've done is fully and completely labeled a potential energy curve. Being able to draw these and label these properly is a huge benefit to you when completing these types of problems. So that wraps up today's video. Today we analyzed potential energy curves, and from a potential energy curve we were able to determine whether a reaction was endothermic or exothermic. We were also able to quantitatively determine the change in enthalpy of the reaction. Also, we looked at forward versus reverse reactions and determining the activation energy in both directions. I'd like to thank Brian Zuthan and Lucas Tien for writing, filming, and editing this video. I'd like to thank you guys for watching it, and I'll see you in the next one.